Hello, thank you for joining us for our presentation, Avoiding the Security Pandemic, Are You Doing Enough? I'm Jerry McGovern, Security Applications Engineer with Tortuga Logic, and I'll be presenting today along with Brian Dickman. Brian will present our first section entitled The Security Pandemic, making the case for the increasing need for improved security assurance. I'll follow with the section Solutions for IP Integrators, where we'll lay out the foundation of a solution to help you improve your security assurance during your IP subsystem, SOC, or system development. Now, let's hear from Brian.
Hi, my name's Brian Dickman. I'm the director and owner of Validity Consulting Limited and a consultant specialising in the field of hardware design verification. We all know that hardware verification is a multifaceted and difficult problem, but there's another highly complex angle to hardware verification that's become increasingly important in recent years, and that is hardware security verification. So much so that we characterise this explosion in cybersecurity attacks as a pandemic in this talk, and it's a word that we've sadly become very familiar with in recent times. So it's something else that hardware verification engineer must account for and needs to have robust strategies and methodologies for. Let's explain what we mean by security pandemic. The last 5 years have seen dramatic increase in number of reported hardware vulnerabilities. So what's behind that? Well, designs are ever increasing in complexity, and smaller geometries allow integration of more and more features and IP on a single chip, as we know. And the incentive for bad actors to break hardware security is high, as exploited vulnerabilities are often hard to fix and may affect systems deployed globally. The trending shift to hardware-based security architectures opens new opportunities for exploitation. And looking at the chart here, you can see data published by MITRE. Compared to 2014, the yearly number of new vulnerabilities has doubled or tripled, and that rate is accelerating. So this is a disturbing trend. A lot can go wrong in hardware. With design complexity comes an equally complex design process. IP blocks come from many sources, both from within and outside of your organization. And some of these blocks are designed with security 10, but others have no notion of security level requirements. So RAM is an example of the latter. And as such, security vulnerabilities are often introduced at various stages of the system development lifecycle. First three items on the list are good examples of places where a vulnerability may be introduced during the system level development. If you're an IP integrator, then you expect secure IP from your IP provider. And IP providers generally will have a security verification process, strategy, methodologies in place. And these processes are tended to verify security at the IP component level. But at delivery, there's still a lot of residual risks remaining that are not maybe intrinsic to the IP. So the IP provider often has little notion of the environment to which the IP will be integrated, and they don't have control of the way in which the integration will be implemented, and implementation can have severe security ramifications. So the IP integrator needs to address this residual risk. So what do we mean by residual risk? So residual risk is a vulnerability that can be introduced by the IP integrator. So poor configuration of the IP block, or an error in the configuration of the IP block, that can introduce a vulnerability into the system at the system level. So that can be caused by an error in the RTL instantiation, such as a connectivity error or incorrect parameterization. It could be incorrect configuration of security features for the application, or it could be errors in the IP configuration from a firmware or a software perspective as well. So some good examples would include, SOC access control to secure asset is misconfigured, allowing untrusted processes access to secure data and controls like trust zone crypto cell in the diagram, for example. Or maybe a failure by the integrator to disable the JTAG interface opening up the a debug vulnerability. Or the operating system might incorrectly map the secure memory page tables, allowing secure data to be exposed to untrusted processes. These residual risks can be at the root of system security problems, and security has conventionally been viewed at the highest abstraction levels. So it's the operating system and the firmware level, and that's where most cybersecurity mitigation effort has been focused historically. However, we're now seeing a growing number of vulnerabilities at the intersection of the hardware and the software, and many of these are exploiting weaknesses in the hardware. Obviously, it's extremely costly and may not even be possible to fix the hardware in the field. So it's really important to get to the root of these risks before hardware makes it into the field and the problem expands geometrically. You really need to look at these residual risks in the context of the entire security ecosystem, all the way through from IP, SOC system to the end customer and products. And customers and emerging industry standards are really driving security requirements these days. Security verification needs to be treated as not as a task, but it really is a journey as you go through transition through these different stages. And each step through that supply chain needs to be accompanied by its own processes to validate security of the overall system. The residual risk to the subsequent level of integration needs to be assessed and documented, and the entire design lifecycle of the product needs a systematic security program. So with that, I'm going to hand over to Jerry, and Jerry's going to talk about the solution for IP integrators.
Thanks, Brian. Now let's take a look at a solution for IP integrators to help address the security pandemic. Given what Brian has just presented, it becomes clear that in order to prevent security vulnerabilities, you need a process to ensure security verification is systematic and effective across the entire development spectrum and involves key stakeholders at all the appropriate times. This process consists of three key components: security requirements, which are collected before or during the early stage of chip design; security verification, where we methodically check those requirements throughout the design process; and security sign-off, in which you confirm those requirements are met prior to tape-out. In its simplest form, these three components comprise a hardware secure development lifecycle. This HSDL fulfills the need for a systematic security program. Let's take a closer look at these key components and the challenges they pose. In order to do successful functional verification, you first decide what you need to test and quantify that in a requirements document. Security testing is no different. You need a comprehensive list of security requirements that is guided by industry standards and knowledge bases. Once those requirements are determined, establish a security verification process that is automated, preferably, and scalable to verify those requirements throughout the chip development. The process should be rigorous and systematic, because your design security is only as good as its most vulnerable component. Finally, our security sign-off procedure should be in place from the design start so that we can track progress, identify security issues as early as possible, and remediate them before tape-out. By the way, this first step, writing security requirements, can be the hardest part in this process. Knowing where and how to start can be difficult, but we'll walk you through some ways to make it easier. What's involved in creating our security requirements? Well, you need to assess your risk in the following ways. First, identify the assets to be protected. Those might be the system configuration and status registers, or the encryption engine, or secure memory, where things like sensitive customer data or encryption keys are stored. Next, determine the product security requirements. That is, those security issues dependent on how and by whom the product is used. These are often prioritized by the severity of risk as it relates to the product use model. For example, a child's toy which contains no sensitive data will have very few security requirements, whereas an aircraft flight control product has serious safety implications which will drive very strict security requirements. And finally, determine the threats to the product security. That is, by what methods can the assets be compromised? Is the threat a physical attack that requires nation-state resources to be successful? Or does the threat come from an internet attack that can be mounted from anywhere by anyone with a computer and determination? All these steps will factor into your list of security requirements. Now, before we proceed to discuss a threat database, it's valuable to understand the definitions of a few words like assets, threats, weaknesses, and attacks. Now, let's focus on two of those. An asset is the thing you want to protect, and a weakness is a condition, event, or behavior that allows an attack to succeed in compromising that asset. The foundation for building a comprehensive security requirements document is the threat database. This is a repository of security threat knowledge and learning. You'll use it as a source for threat modeling for all security critical products, and it creates the focus for our security verification. Every security team should have one, and it can be different for each type of product and use model. It contains the list of relevant enumerated weaknesses, threats, and attacks pertaining to your product. A threat database is the critical internal security asset for an HSDL. The MITRE Hardware Common Weakness Enumeration Database is an excellent start for your security requirements and can form the core of your own internal threat database. If all you do is cover the CWEs relevant to your product, you've made a great start in defining your security requirements. CWE is a publicly available database of common software and hardware weaknesses that have security ramifications. It is contributed to by several dozen companies, including Tortuga Logic, and is maintained by MITRE Corporation. As such, it's a convenient vehicle for communication and coordination of security issues amongst the various stakeholders. You can think of it as a unifying language for security program participants who normally use different terminologies. Through detailed descriptions of security weaknesses, CWE enables a systematic methodology for threat modeling and validating the chip security with rules-based verification. CWE provides a basis for security sign-off through precise metrics to track progress and compliance with security requirements. It keeps the focus on threats and their mitigations. The CWE and the threat database you build from it lay the foundation for a rules-based approach to security verification, the second component of our HSDL. Each weakness will correspond to one or more rules for security behavior that must be enforced. These security rules are then applied to your verification tests, where violations are flagged for analysis. Security verification needs to be scalable and automated so that we can continually monitor the security state of the design as it's developed. Scalable in order to be able to verify issues from IP integration at the block level to software configuration of the IP using an emulation environment, for example. Automated so that you can regularly regress your security tests, allowing you to find and remediate vulnerabilities quickly when they are introduced by design changes. But traditional verification methods for security analysis are, for the most part, neither scalable nor automated to the extent needed. Our HSDL needs something to fill the gaps left by traditional methods and drive this rules-based approach. Information flow analysis is a tool that's well suited to security verification and fills these gaps. So what is information flow analysis? It's the automated tracking of data from a source and/or to a destination. This is a symbolic analysis that's independent of the specific values of the asset data, so it can be tracked through both logical and sequential transforms. This is particularly important for security verification when you don't care what the values are that are leaked, but whether or not they leak at all. In information flow analysis, control signals are analyzed in the context of the simulation as to how they affect the information flow. The result is, if there is a path for the source to affect the destination, and it's enabled, information flow analysis will find it. This is very powerful when applied to secret assets, as it enables our rules-based approach without requiring traditional methods like checkers, scoreboards, and exhaustive stimulus. In fact, these traditional methods would be very difficult to apply to secure data tracking, if not impossible. Combining the power of information flow analysis with the scalability of a rules-based approach to security verification gives you the ability to analyze that hardware-software boundary for vulnerabilities you might not find any other way. Finally, information flow analysis is very well suited to finding unknown and unexpected vulnerabilities. You can use an open-ended rule to explore all possible destinations of a given secure asset. As applied to security verification, traditional approaches are important, but may leave gaps when dealing with system complexities. Each of these traditional approaches has limitations in repeatability, scalability, or coverage. Information flow fills these gaps and supplements your existing verification methods to help you attain complete coverage that is repeatable and scalable. We have found that adding information flow analysis to security verification is an important component to an efficient and effective HSDL. The final component of the HSDL is security sign-off. Now we show it here at the end of the process, but it's actually a continuous task that begins when the security requirements have been determined. The security requirements provide the means by which the progress of the security verification phase is measured, and the final security sign-off occurs when key stakeholders agree that the requirements have been verified. The design is going to evolve through bug fixes and security remediation during verification, so security requirements may need to be adjusted or reprioritized, and that requires the involvement of the stakeholders. So we see that security sign-off as a continuous monitoring process is crucial to a complete security program. A hardware security design lifecycle is essential to mitigate residual risks and prevent security vulnerabilities from propagating through the supply chain to your customers. In our experience, most security teams aren't confident they're doing enough to prevent security leaks. Now, if you are doing enough, it's probably because you're doing these three things in a way that scales to meet the unique challenges of security and system-level verification. First, you've started with comprehensive security requirements, guided by the Common Weakness Enumeration Database. Second, you've systematically applied a variety of methods, including information flow analysis, to close all gaps in security verification. And third, you validate compliance with security requirements and characterize residual risk for system and software integrators through a continuous security sign-off. Applying this HSDL methodology to your security verification efforts will give you the confidence that you are doing enough. For more detailed information on these important concepts, please visit the links provided here. If you have questions or comments about this presentation, Brian and I would both love to hear from you. Thank you for attending our presentation.